Okay, let's unpack this. You step onto an aircraft, or maybe drive over a towering bridge. You trust, implicitly, right, that the structure beneath you is sound, free from, hidden weaknesses. But how do we actually know? How are those invisible flaws caught before they become, well, catastrophic problems? Today, we're taking a deep dive into the world of non-destructive testing, specifically focusing on radiographic testing, or RT. We're using a really comprehensive source document here, rt01.pdf. Our mission really is to give you a shortcut to understanding what NDT is, why it's so vital for safety, for quality, its surprising history, and the intricate details behind managing it today. Get ready for some genuine aha moments.
Yeah, it's remarkable, isn't it, how foundational this field is. NDT is deeply intertwined with pretty much every aspect of industrial safety and product integrity. It pulls from physics, engineering, even international standards. It's kind of a silent guardian,
Well,
keeping our modern world running safely and reliably.
So for those of us familiar with the field, we know non-destructive testing, NDT, is about examining a material without messing up its future usefulness. It's the opposite of those destructive tests, where you basically break something to see how strong it was. NDT checks it, then it goes right back into service. But the fascinating nuance, and our source points this out, is in that definition of future usefulness.
Right. Like non-invasive medical diagnostics x-rays, ultrasound, they fit perfectly. Used in medicine, used in industry. But it gets a bit gray. What if you take a tiny sample for, say, electron microscopy? The main part is fine, but that specific sample, it's gone, right, for its original purpose anyway.
Or you run a test on some fluid, spectroscopy maybe, but then you pour that sample down the drain.
Exactly. The sample itself isn't useful anymore, so it hinges on whether that specific tested item can go back to doing what it was meant to do.
Okay, that clarifies things.
And it broadens the perspective, doesn't it? NDT isn't just, oh, look, a crack. It's more strategic. It's about understanding the material properties to stop issues before they start. Our source details how it looks for common things like porosity or walls thinning from corrosion, disbonds.
It is so.
But it also covers non-destructive material characterization. That lets us check things like how well resin has cured or the depth of case hardening, even internal stress.
Wow, so much more than just flaw detection.
Absolutely. These factors directly impact how long something will last in service.
So why the big investment then? Why has NDT become such an indispensable tool? You mentioned it wasn't always this way.
Well, a big driver is just the increasing demands we place on machines and structures. Think about it. Designers push for lighter parts, often using new alloys, composites.
Things we don't always fully understand initially.
Sometimes, yeah. And it means components are under higher stress, more prone to fatigue, safety factors might be lower. Our source mentions aircraft parts failing back in the day because the characteristics of certain alloys weren't fully known. Tragic stuff. So NDT became crucial.
Yeah, so higher demands. What else?
Engineering demands for just, well, sounder materials. As parts get more precise and safety margins shrink, you need better control over raw materials, higher quality manufacturing.
Makes sense. Customers expect it too, I imagine.
They do. And public safety plays a huge role. Think court cases after failures, the push for car safety features like airbags, oversight from bodies like OSHA, the FAA.
Right, regulation.
And public perception. The source notes how passengers have literally canceled flights after accidents. That hits the bottom line hard.
And then there's just the cost of failure itself. It must be astronomical sometimes.
Oh, enormous. Forget the human tragedy and legal costs for a second. Just think financially. Replacing complex parts, the labor, and the domino effect. Our source gives this example. One broken machine in a high-speed production line. It can shut the entire operation down. The economic ripple effect is just profound.
Which brings us to that key question you touched on. Is NDT a cost, or is it really an investment?
It's a critical question, and honestly, in some industries, like heavy metals perhaps, it's still seen reluctantly just as a cost center. And when production struggles, guess what's often the first corner cut?
Let me guess. NDT.
You got it. There's subtle pressure sometimes on technicians to just pass things, maybe things that aren't quite up to standard.
That sounds risky.
It is. But the source makes a really strong argument here. NDT should be used as control mechanism to make sure manufacturing processes stay within the design requirements. It should never be like a last-ditch quality check at the end of the line. That's not how it works best.
So using it proactively.
Exactly. When you do that, it actually saves money, it boosts the company's reputation, and ultimately it adds to the profits. It's definitely an investment.
Okay, a strategic investment. Yeah. And like any investment, you need the right tools. The NDT world isn't just one thing, is it?
Not at all. It's incredibly diverse. Our source mentions 6 main categories: visual, penetrating radiation, magnetic, electrical, mechanical vibration, thermal, and chemical, electrochemical.
Wow, quite a range.
Yeah, from just looking closely, maybe with a borescope, to using liquid penetrant for surface cracks, or magnetic particles for steel,
Right, MP testing?
or eddy current for conductive materials like inspecting heat exchanger tubes. Then you have ultrasonics, using sound waves for internal stuff, leak testing, acoustic emission for listening to materials under stress.
Listening, like for crack growth.
Precisely. And infrared or thermal methods looking for heat flow issues, like loose electrical connections. It's a whole toolkit.
And each tool has its place.
Exactly right. No single NDT method reveals everything. Our source is very clear on that. The real skill is picking the right tool, or maybe combination of tools, for the specific job. You need to consider the material, the type of flaw you're hunting for, the part's shape, all of that.
And that selection process brings us to our main focus today, radiographic testing.
RT?
Ah, yes, the star of the show.
It holds a pretty unique position in NDT, doesn't it? Often seen as maybe the most universally effective, due to its wide use and acceptance.
It definitely has compelling advantages. It lets you see inside things, internal discontinuities. It can show up significant variations in composition. And crucially, it gives you a permanent record, usually on film or increasingly digital images. That's huge for documentation and review.
Okay, sounds powerful, but there must be downsides.
Oh, absolutely. It's not cheap. The
Okay.
equipment, the dedicated space you often need. It's a big capital investment. And its effectiveness, its ability to find things, really depends on the angle of the radiation beam. It's best at seeing features, like cracks, that have a thickness change parallel to that beam. Orientation matters.
Very much. You also generally need access to both sides of the part for the radiation to pass through.
Right, source on one side, detector or film on the other.
Exactly. And the big one, the most critical limitation perhaps, is radiation safety. It uses ionizing radiation, so it demands really rigorous safety measures. It's a highly regulated process for a very good reason.
Okay, so powerful but complex. To really appreciate RT, we need to go back in time, don't we? To 1895, a chilly Friday afternoon.
We do. November 8th, 1895, University of Würzburg, Germany, Wilhelm Conrad Röntgen.
He's messing about with a cathode ray tube. It's covered. And he notices this screen nearby, barium platinocyanide. It's glowing.
Exactly. An odd luminescence. And he knew right away these couldn't be cathode rays. They just don't travel that far in air. He was instantly hooked.
And he quickly figured out these new rays could pass through stuff. Paper, wood.
Metal, even flesh, creating these shadow pictures. But here's a surprising detail from the source. Röntgen himself was skeptical at first.
Really? After seeing that?
Yep. He spent 7 intense weeks just studying them, apparently telling a friend, "I have discovered something interesting, but I do not know whether or not my observations are correct." Very cautious.
Wow. And then came the famous X-ray of his wife's hand.
Bertha's hand, yes. December 1895, a 15-minute exposure. Legend has it, he told her, "Now the devil will be to pay." He sort of knew his life, and science was about to change dramatically.
A premonition.
You could say that. And what's striking is how fast the news spread. It was an immediate global sensation, not just in science labs, but in the popular press, too. An article in the Vienna press really kicked it off. Within days, scientists everywhere were replicating his results. It was viral, 1895 style.
Amazing speed. And Röntgen himself, he was quite humble about it all.
Remarkably so. Declined most honors, refused the von title that would have made him nobility, and crucially, he refused to patent X-rays. He believed discoveries belonged to humanity.
That's quite something. But not everyone shared that idealism, especially with something so potentially revolutionary.
Not entirely, no. Our source brings up Thomas Edison. Edison famously said something like, "After someone discovers something wonderful, someone else needs to look at it commercially. How can we use it, profit from it?"
So Edison jumped right on it.
Pretty quickly. Developed brighter X-ray tubes, fluoroscopes, was exhibiting them publicly by May 1896. The commercial push was immediate.
Interesting contrast.
And it also highlights that, other people were probably generating X-rays before Röntgen without realizing it.
Like who?
Well, crooks, back in the day, kept complaining about photographic plates getting fogged, probably X-rays. And even more specifically, the source mentions Arthur Goodspeed and William Jennings at the University of Pennsylvania. In 1890, 5 years before Röntgen, they accidentally made a radiograph of some coins.
No way. Did they know what they'd done?
Not at the time. They just filed it away. Only after Roentgen's announcement did they look back and realize, hey, wait a minute.
That accidental discovery really sets the stage, doesn't it, for deliberately using these rays for inspection?
It does. And things moved fast. 1898, just 3 years after Röntgen, Marie, and Pierre Curie discovered polonium and radium. That laid the groundwork for using gamma rays, another form of penetrating radiation, for radiography.
So X-rays and gamma rays.
Right. And a huge leap for X-rays came in 1916. William D. Coolidge, working for General Electric, invented the hard vacuum hot cathode X-ray tube.
What did that change?
Made things much more reproducible, easier to operate, and allowed for higher energy X-rays, really crucial for industrial applications.
And who really pushed it for NDT in industry?
A key figure mentioned in our source is Horace Lester at the Watertown Arsenal. His work in the 1920s really showed that X-rays could find those internal flaws in castings and welds, the kind causing premature failures.
So he proved its practical value for preventing disasters.
Definitely. Although, interestingly, even Lester noted back then that using radiography for 100% inspection rarely made economic sense. That cost-benefit tension has always been there.
Huh. Some things don't change.
Indeed. And it was in this growing field, right before World War II, actually, that the American Society for Non-Destructive Testing, ASNT, was formed, 1941.
Just in time for the war effort.
Exactly. The war, with its massive need for reliable equipment, really gave ASNT a push. It became this vital hub for sharing information, for education, and eventually for certifying personnel.
And they've championed RT over the years.
Oh, absolutely. Leading to some amazing applications, inspecting priceless things like the Vatican Pieta, the Liberty Bell, even parts of the U.S. Capitol building.
It's incredible, isn't it? The same tech checking jet engines is also looking inside the Liberty Bell. That really shows the range. But running an RT program, whether for a bridge or a priceless statue, it can't be simple. There must be a ton to consider.
A labyrinth is a good word for it. Our source actually breaks it down into 6 basic management questions you have to ask up front.
Okay, like what?
Things like, what are the regulatory requirements? How big is this program going to be? What about safety and environmental impact? What's the timeline? Is there a clear cost benefit? And, crucially, do we have the resources, people, money, to actually do it?
You've got to answer those first.
Before you even think about buying equipment. Then, you generally have 3 main ways to implement it.
Which are?
You can hire a specialized service company, you could bring in consultants to help set it up or oversee things, or you develop your own in-house program.
Pros and cons to each, I assume.
Absolutely.
Okay.
With service companies, for example, you need to nail down the contract type, time, and materials, or a fixed scope. Who's watching the clock and the budget? Who writes the actual test plan? Who signs off on the results?
And who's ultimately liable if something is missed?
That's the million-dollar question, isn't it? Who is technically qualified to approve the work scope and who carries the liability? These details are critical no matter which path you take.
Okay, so assuming you figure out the who and how, the actual doing needs structure too, right?
Yeah.
Procedures seem key.
Cannot overstate their importance. Technical procedures are basically the written instructions. Codes and specs often require them. They can range from general guidelines to super detailed, step-by-step processes for a specific part.
What goes into a typical procedure?
Our source outlines a common format: purpose, scope, references, definitions, then crucial bits like personnel requirements, equipment needed, safety issues, big one. They're the actual test steps, how to judge acceptable versus unacceptable acceptance criteria, reporting requirements, and any attachments like diagrams.
It's the playbook, everyone on the same page.
Exactly. Ensures consistency, reliability. And speaking of personnel, qualification is absolutely vital.
Why so critical?
Because NDT is what's called a special process. Its adequacy, whether the test was done right, is often hard to tell just by looking at the result. It depends massively on the skill and knowledge of the person doing the test.
The inspector.
Right. And ASNT, the American Society for Non-Destructive Testing, is a world leader here. They provide guidelines like SNT TC1A, national standards like ANSI SMT CP 189, even third-party certification programs like ACCP.
So there are defined levels of qualification.
Oh, yes. For RT, for example, a Level I technician needs specific classroom training hours plus months of on-the-job experience. A Level 2 needs more training and experience building on Level 1.
Then they have to pass exams.
Comprehensive ones. general knowledge, specific knowledge about the RT method, and a practical hands-on exam. Plus, they need annual vision tests. It's rigorous.
Okay, competence is covered. But you mentioned safety earlier, especially with RT. That sounds paramount.
It's the first obligation, always, especially with ionizing radiation. Setting up an RT program means identifying all the applicable rules and codes, providing the right safety gear barriers, maybe hard hats, steel-toed shoes.
Standard PPE plus radiation specifics.
Yeah, exactly. Thorough radiation safety training is non-negotiable. Before any test, you do a visual survey for hazards. You notify everyone working nearby. Check for explosive atmospheres if relevant.
Common sense, but critical.
Absolutely. Never enter restricted radiation areas without authorization. Remove personal metal items if you're near high-voltage equipment. Know the emergency evacuation plans. And critically, unqualified personnel must never operate the radiation-producing equipment, ever. Because radiation can harm people silently, these extra steps aren't just nice-to-haves, they are essential.
Got it. Safety first, last, and always.
Precisely. And even with qualified people following procedures safely, we still need to think about the reliability of the results.
What do you mean?
Well, there are basically 4 outcomes when you do a test. You find a discontinuity that's actually there, good. You correctly identify that there's no discontinuity, also good.
Okay.
But you could miss a discontinuity that's present, that's bad, potentially catastrophic, or you could make a false call, say there's a flaw when there isn't one.
Which means rejecting a perfectly good part.
Exactly, leading to waste, unnecessary cost. So the source talks about this balance. A reckless inspector might accept flawed parts. A too conservative one rejects good parts. Neither is good for business or safety.
Tricky balance.
It is. The goal is a high probability of finding everything you need to find, with basically 0 misses and 0 false calls. The challenge is ensuring inspectors are both skilled and motivated to perform at their best, consistently.
Okay, moving from the practicalities of running a program to the nitty-gritty science. Let's talk units. How do we actually measure radiation in this field?
Yeah, the numbers part. It's important for consistency. Here we get into the International System of Units, SI.
The modern standard.
Right. Established back in 1960, the goal was one single coherent set of units for all of science, engineering, the public, and the confusion between, say, scientists using centimeters and grams and engineers using something else.
I think simpler.
Hopefully. But before SI, and you still see them sometimes, radiography used traditional units. The Curie, the Röntgen, the Rad, the Rem.
Names I've heard.
Yeah, and our source points out they were often based more on observation than, precise physical phenomena. A Curie, for example, was originally defined relative to 1 gram of radium, not super precise.
So SI units replace these. How does that work?
Okay, so the Becquerel BQ replaced the Curie. The Curie was tied to radium's activity, about 37 billion disintegrations per second. A Becquerel is much simpler, just 1 disintegration per second. We often use gigabecquerels, GBQ, billions of BQ, to get practical numbers for source strength.
Simpler definition.
Then the coulomb per kilogram, CK replaces the Röntgen. The Röntgen was about how much ionization X-rays caused in a specific volume of air. The SI unit defines it by the electrical charge produced per unit mass of air. More fundamental.
Got it. What about Rad and Rem?
Right. The gray, Gara replaces the Rad. The Rad was a measure of absorbed dose, how much energy was deposited in material based on an old energy unit, the erg. The gray is also absorbed dose, but defined cleanly in SI terms. 1 joule of energy absorbed per kilogram of matter.
Joule per kilogram.
Here.
And the Rem.
The Sievert, SV replaces the Rem. The Rem stood for Röntgen equivalent man, trying to quantify the biological effect on humans. The Sievert also measures dose in joules per kilogram, like the gray.
Wait, same units?
Same base units, JQG, yes. But the Sievert includes crucial quality factors. These account for the fact that different types of radiation, alpha, beta, gamma, X-rays, have different biological impacts, even if they deposit the same amount of energy.
So the Sievert is specifically about biological risk to humans.
Exactly. It's a measure of dose equivalent weighted for biological harm. So moving from Curie, Röntgen, Rad, Rem to Becquerel, Coulomb per kilogram, Gray, and Sievert gives us a much more precise, physically grounded, and internationally consistent way to talk about radiation activity, exposure, absorbed dose, and biological effect.
Makes sense why NIST and others strongly discourage using the old units now.
Absolutely. It's about clarity and safety on a global scale.
Wow. From a curious glow in a German lab all those years ago to these incredibly precise international standards guiding global safety, the journey of radiographic testing is, Was really incredible. So what did this all mean for you, our listener?
Well, it means that the integrity, the hidden soundness of so much of our modern world, the planes you fly in, the bridges you cross, the power plants providing energy, even the safety of workplaces relies heavily on these NDT principles and practices we've just unpacked, specifically RT in many cases. Understanding even a little about these hidden inspections gives you, I think, a whole new appreciation for the quality and the safety that's built into the world around us, often unseen.
It really does. Think about that for a moment. How much we trust in the unseen, these invisible assurances that NDT provides every single day.
So here's a thought to leave you with. What other invisible systems, what complex processes do you rely on daily without maybe realizing the depth of science, management, and frankly, human diligence that makes them work safely? We hope this deep dive has given you a newfound appreciation for the hidden but vital world of NDT. Thanks for joining us.